I'm Elaine, and like Alyssa, I work with Dr. Alex Hansen, also in Power. And building off of what Alyssa's saying, my project and what I'm going to talk about is core materials for integrated on-chip inductors. And I'm going to skip, oh, actually, wait. Oh, here we go. And I'm going to skip some of the motivating material. Alyssa said, usually in power converters, magnetic components are huge, and we're trying to make them really small. And in the spirit of Moore's law, it'd be really nice if we had some way to basically print billions of tiny on-chip inductors like we do for MOSFETs. And in order to do that, as Alyssa said, in order to make these inductors as small on the chip scale, we have to operate power converters at really high frequencies. And for chip scales, that typically means like above a few megahertz, like a few megahertz, 10 megahertz, and above that. And the main bottleneck for magnetic components at these high frequencies are the core materials available now for power. Because conventional, basically in power, we always typically use ferrites actually, even in lower frequency stuff. And all of the conventional ferrites have too much core loss, so we can't use them. So my research is basically what's a better core material for this particular application. And a good material for a core for an on-chip inductor should have high permeability, again, because the inductor's main function, well, the main function of the core of the inductor is to contain flux. It should have high saturation C or magnetization, because again, as Alyssa said, we don't really want to saturate a core. Also because we want particularly high permeability for the core to function. So once the core saturates, you don't have permeability anymore. I'll talk a little more about losses. So in power, we care about two particular contributions to core loss. One is eddy currents, and eddy currents just come from Faraday's law. Whenever you throw flux into a material, you generate a voltage to oppose it because of Faraday's law, and that voltage causes eddy currents to circulate within the material. And these currents are usually really bad because they don't actually deliver power. They just sort of exist in the material and dissipate as heat. So actually for core materials, you don't want anything that's really conductive. You want something that has very high resistivity. The other contribution to core loss is hysteresis, which is just the area inside your MH or BH curve. And generally you want this area to be as small as possible. So low corrosivity, low remanence, all that. And specifically for the case of on-chip integrated inductors, we want something that's compatible with CMOS, which means that we're limited to fabrication techniques with that are low temperature, below like 450 degrees C. And here is a comparison of basically what researchers have done for on-chip inductors in terms of core materials. So I mentioned ferrites because, again, power people have been using ferrites for decades. And there are ferrites that can operate at high frequency, like Alyssa said, like nickel zinc. But the main problem with ferrites is that they're not compatible with CMOS, because in order to make most ferrites, you have to anneal them at temperatures of like 1,000 degrees C, and that just doesn't work with CMOS. People have also tried using thin film magnetic alloys like permalloy, and these are usually okay. They have generally great magnetic properties like good permeability, pretty high saturation, but they suffer from core loss, or specifically eddy currents loss, because these materials are generally very conductive, so lots of eddy currents, and that's really bad. Unlike ferrites, they're actually very compatible with CMOS because you can just electroplate them because they're just metals. And like Alyssa said, a lot of people in this space have tried using air core, meaning no core, and generally you have very limited performance because air doesn't have great permeability, but people still use it anyways. So The field of on-chip inductors, specifically core materials for on-chip inductors, is really limited by the available core materials we have right now. And the rest of my talk is just about a promising class of materials called, in what we call in power, nanogranular materials or nanocrystalline materials. And basically they check all the boxes we want. And I'm just going to focus on one particular nanogranular material, cobalt zirconium oxide. And cobalt zirconium oxide consists of these cobalt grains that are nanoscale. They have to be nanoscale so that they're small enough to not have that much eddy currents flowing inside them, which leads to its high resistivity. These cobalt grains are surrounded by an inactive insulating zirconium oxide, and that's generally how these nanogranular materials work. You have like these very small magnetic grains, nanoscale grains, inside this matrix of insulator. Cobalt zirconium oxide has, again, all the properties we like, and in particular, it's deposited by reactive sputtering, which is compatible with CMOS, but it is very slow. So this particular group that did make on-chip inductors with cobalt zirconium oxide, they had a deposition rate of around 20 nanometers per minute, which is equivalent to 1.2 microns per hour. And to give you a rough estimate, these inductors typically are like 40 microns thick. So it takes a very long time to grow these inductors. One way to address that is to look at other faster deposition techniques, such as high power impulse magnetron sputtering, which is what we're doing. The other problem about growing cobalt zirconium oxide is that it's kind of difficult to get films with the properties we like. So here are examples of good films, like MH loops of good films. They have pretty low corrosivity, below 50 worsteds along either axis. And kind of to your point, because in power we care about low core loss, it's like the biggest thing. We like to excite our materials along their harder axes. And in that spirit, we also like materials with strong anisotropy, so that the harder axis is like very hard, has low corrosivity and all that. And it's actually pretty easy to get MH loops that don't look like the previous slides, that have higher hysteresis loss. One way you can do that, or one way that causes that, is if you grow films with a lot of PMA and stripe domains, which are kind of correlated. So if you ever see stripe domains in your MF image, or sort of column structures in your TEM image of these films, then typically the MH curves look like the ones on the right, where you don't have very strong anisotropy. You sort of get a mixed behavior in both axes, which generally means that the loops look wider in both axes and equates to more hysteresis loss, which is generally what we don't want. And how did this happen? There are many factors that can cause a lot of PMA and these column-like structures. One way that this particular group found these structures is by increasing the sweater pressure. So if they found that if you use too high of a sweater pressure, you get these column-like structures, but if you keep the sweater pressure low, you get a nice uniform grain structure and happy loops. There's also a very narrow range of chemical compositions for cobalt zirconium oxide that have the properties we like. And that's typically around 60% cobalt, 10% zirconium, and 30% oxygen. If you're outside this range, again, you get these column-like structures in PMA. If you actually have too much oxygen, the oxygen starts oxidizing the cobalt and the entire material becomes more paramagnetic, which is also not what we want. And it's kind of a brief summary of now of like the state of research on on-chip inductors right now. In general, people have made on-chip inductors with these nanogranular materials, specifically cobalt zirconium oxide, and with relative success, actually. This group has made a converter with 90% efficiency using these inductors, which is like higher than the efficiencies of on-chip integrated power converters you'll find on the market, which are typically around like 60 to 70%, so much higher. But the limiting factor right now is that we in Power don't really understand core materials. So there needs to be a lot of work in modeling core materials and also coming up with faster fabrication processes than reactive sputtering to make these core materials, which is the whole point of my project. So that's it, yeah.